So function f of x is said to be even if f of minus x is equal to f of x. For example, x square. So in x square, if we replace x by minus x, then it will be minus x whole square. So it will be x square. Therefore, it is f of x. Therefore, in this case, f of minus x is equal to f of x. Therefore, we can say that x square is an even function. Now function is said to be odd function if f of minus x is equal to minus f of x for all x. For example, x cube. So in x cube, if we replace x by minus x, then it will be minus x whole cube. So it will be minus x cube. So it will be minus f of x. Therefore, in this case, f of minus x is equal to minus f of x. Therefore, we can say that x cube is an odd function. Now, if function is even, then integration from minus L to L f of x dx can be written as twice integration 0 to L f of x dx. And if function is odd, then integration minus L to L f of x dx will be 0. So we will use these properties in the example. Now we know that Fourier series of function f of x in the interval minus L to L is given by f of x is equal to a0 divided by 2 plus sigma n equal to 1 to infinite an cos n by x divided by L plus sigma n equal to 1 to infinite bn sin n by x divided by L, where a0 is 1 divided by L integration from minus L to L f of x dx, and an is 1 divided by L integration minus L to L f of x into cos n by x divided by L dx, and bn is 1 divided by L integration from minus L to L f of x sin n by x divided by L dx. So this is how we can find out the value of a0, an and bn. Now let us discuss case 1 when function is an even function. So when function is an even function, then we know that integration from minus L to L f of x dx will be twice integration from 0 to L f of x dx. So here we know that a0 is given by 1 divided by L integration minus L to L f of x dx. But here function is an even function, therefore a0 will be 2 divided by L integration 0 to L f of x dx. Now, how to find an in this case? So we know that an is given by 1 divided by L integration minus L to L f of x into cos n by x divided by L dx. But here f of x is an even function and cos is even function. So the product of two even function is even. Therefore, an will be 2 divided by L integration 0 to L f of x into cos n by x divided by L dx. Now, how to find bn in this case? So, we know the formula of bn, that is 1 divided by L integration minus L to L f of x into sin n by x divided by L dx. And here f of x is an even function and we know that sin is odd function. So, the product of an even and odd function is odd. Therefore, bn will be 0. So, whenever function is an even function, then no need to find out bn because bn is 0. So, whenever function is an even function, then we will find out a0 and an. Now, let us discuss second case. When function is an odd function, then we know that integration from minus L to L f of x dx is equal to 0. So, here we will have to find out a0 in this case. So we know the formula of a0, which is 1 divided by L integration from minus L to L f of x dx. But here f of x is an odd function, therefore integration minus L to L f of x dx will be 0, therefore a0 will be 0. Now we will have to find out an for this case. So what is the formula of an? It is 1 divided by L integration from minus L to L f of x into cos n by x divided by L dx. So here f of x is an odd function and cos is even function. So the product of an odd function and even function is odd. Therefore, an will be 0. Now we will find out Bn for this case. So we know the formula of Bn, that is 1 divided by L integration from minus L to L f of x into sin n pi x divided by L dx. So here f of x is an odd function and sin is also odd function. So the product of two odd function is even. Therefore, Bn will be 2 divided by L integration from 0 to L f of x into sin n pi x divided by L dx. So whenever function is an odd function, then no need to find out a0 and an, because a0 and an are 0. So we will find out only Bn, which is given by 2 divided by L integration 0 to L f of x sin n pi x divided by L dx. Now, if the function is neither even nor odd, then we will have to find a0, an and bn. So, if function is neither even nor odd, then we will have to find out a0, an and bn. Now, let us discuss example related to this. So, first example, find the Fourier series of the function x minus x cube in minus 1 less than x less than 1. So here first of all we will have to check whether the function is even or odd. So here f of x is equal to x minus x cube. So now we will replace x by minus x. So here it will be minus x minus x whole cube. So it will be plus x cube. Now taking minus common from these two. So minus in bracket x minus x cube. So what is x minus x cube? It is function. So this can be written as minus f of x. So as we have studied definition of odd function, if f of minus x is equal to minus f of x, then function is called odd function. Therefore, f of x is an odd function. Now, as we have discussed earlier, if f of x is an odd function, then no need to find out a0 and an, because a0 and an will be 0. Hence here a0 and an will be 0. Therefore, we will find out value of bn only. Now first of all, we will have to find the value of L. So comparing minus 1 to 1 with minus n to n, we will get L is equal to 1. Now we know that the Fourier series of an odd function with period 2n is equal to 2 is given by f of x is equal to sigma n equal to 1 to infinite bn sin n pi x divided by n. So here we will have to find out value of bn. So here value of n is 1, therefore it will be sigma n equal to 1 to infinite bn sin n pi x divided by 1, so it will be n pi x. Now bn is given by 2 divided by L integration from 0 to L f of x sin n pi x divided by L dx. Now we know that in this example value of L is 1, therefore bn will be 2 integration from 0 to 1. What is f of x? It is x minus x cube sin n pi x dx. Now here as you can see that there are two functions. So here we will use Bernoulli's formula. But before applying Bernoulli's formula, we will have to choose one function whose successive differentiation is 0. So here we will choose x minus x cube because its successive differentiation is 0. So here first function will be as it is, then we will take integration of second function, then minus sign, then we will take derivative of first function, then integration of second function. So this is how we can apply Bernoulli's formula. So here first of all 2 will be as it is in bracket, first function x minus x cube will be as it is and second function was sin n pi x. So we will have to take integration of sin n pi x. So what is integration of sin theta? It is minus cos theta. Therefore integration of sin n pi x will be minus cos n pi x divided by n pi because coefficient of x is n pi. Then minus, now we will take derivative of this function. So here derivative of x will be 1 and derivative of x cube will be 3x square. Because we know that derivative of x raised to n is n into x raised to n minus 1. So here in bracket 1 minus 3x square. Now we will take integration of this bracket. So integration of cos theta is sin theta. Therefore, integration of cos n pi x will be sin n pi x divided by n pi, because coefficient of x is n pi. So here it will be minus sin n pi x divided by n square pi square, because n pi into n pi will be n square pi square. Now plus, now we will take derivative of this bracket. So here first term is 1, so derivative of 1 is 0. And here derivative of x square will be 2x. So 2x into 3, so here it will be 6x. So here it will be minus 6x because of this minus sign. Now we will take integration of sin theta. So integration of sin theta is minus cos theta. So integration of sin n pi x will be minus cos n pi x divided by n pi, because coefficient of x is n pi, and here n square pi square into n pi, so it will be n cube pi cube. Therefore here cos n pi x divided by n cube pi cube, because minus minus it will be plus. Now minus, we will take derivative of this bracket. So here derivative of x is 1, so minus 6 into 1, so it will be minus 6. Now we will take integration of this bracket. So integration of cos theta is sin theta. So here integration of cos n pi x will be sin n pi x divided by n pi. So here it will be n cube pi cube into n pi. So it will be n raised to 4 into pi raised to 4. So it will be sin n pi x divided by n raised to 4 pi raised to 4, and limit will be from 0 to 1. Now here first of all we will replace x by 1. Then we will replace x by 0. So here if we replace x by 1, then here 1 minus 1 will be 0. So no need to write down first term. Now here think about second term. So here if we replace x by 1, then here it will be sin n pi, and value of sin n pi is 0. So no need to write down second term also. Then here if we replace x by 1, then here it will be minus 6 into 1 into cos n pi divided by n cube pi cube, and here sin n pi, and value of sin n pi is 0, so no need to write down this term. So for upper limit it will be 2 in bracket minus 6 cos n pi divided by n cube pi cube. Now here if we apply lower limit, then for that replacing x by 0, so 0 minus 0, so this term will be 0. And here if we replace x by 0, then value of sin 0 is 0, so no need to write down the second term. And here minus 6 into 0, so this is also 0, so no need to write down third term. And here sin 0, and sin 0 is 0, so no need to write down this term also. Therefore final answer will be 2 in bracket minus 6 cos n pi divided by n cube pi cube. Now here we know that value of cos n pi is minus 1 raised to n. So final answer will be minus 12 into minus 1 raised to n divided by n cube pi cube. So this is the answer of B. But here we will have to find the Fourier series of the function in minus 1 less than x less than 1. So Fourier series is given by f of x is equal to sigma n equal to 1 to infinite bn sin n pi x. Now we will put value of bn in this Fourier series. So here it will be sigma n equal to 1 to infinite minus 12 into minus 1 raised to n divided by n cube pi cube into sin n pi x. Therefore, Fourier series of this function will be minus 12 divided by pi cube sigma n equal to 1 to infinite minus 1 raised to n divided by n cube into sin n pi x. So in today's lecture, we have discussed about Fourier series of even and odd function, and we have discussed one example of odd function. In this example, we have discussed how to find the Fourier series of an odd function. Thank you for watching this lecture. I will see you in the